All right, so today we're going to talk about solubility and expressing solubility. We've already talked about what a solution is and how we can express how concentrated it is. But today we're going to talk about solubility itself. So, uh, as a definition of solubility, solubility is just a measure of how much solute dissolves in a solvent, usually expressed in grams of solute per 100 grams of solvent. So if we've seen this sort of a graph before, just a whole lot of different salts, from sodium nitrate, calcium chloride, table salt, a whole bunch of different salts here, showing that how much they dissolve in 100 grams of water at different temperatures. So for example, at 20 degrees Celsius, it looks like we can dissolve about 35 grams of table salt, sodium chloride, for every 100 grams of water that we have. And we normally think of table salt as becoming much more soluble at higher temperatures because we think about, like, throwing some salt into some water when we're, making pasta or something like that. It does dissolve relatively quickly at higher temperatures, but it's not as dramatic as a lot of other salts are. You can see, for example, potassium nitrate solubility shoots up as temperature increases. But that's what solubility measures. Now, a couple of definitions here, a couple terms. A saturated solution, if you recall, is a solution where essentially what it looks like is you'll have some undissolved salt at the bottom of the beaker, okay? And at that point, dissolving, so going from crystal to aqueous, going from solid to aqueous, is at equilibrium with crystallization. So there will be some ions leaving the solid state and entering the aqueous state, and then some aqueous ions sort of randomly finding each other and reattaching and forming crystals. And so they'll be at equilibrium, which means you'll have some solid, usually sitting at the bottom of the glass. Unsaturated simply means that we could put more in there. There's room for more. So there, you're not at equilibrium because you don't have enough ions in aqueous state to sort of reform those crystals. And then finally, supersaturated is kind of an interesting state because it's where we have more solute than we would expect at that temperature. So if we think about it in terms of our graph, let's talk about, well, we'll just stick with the black line here, sodium chloride, and let's say we're at 90 degrees. If I only have 30 grams of table salt dissolved in 100 grams of water at 90 degrees, well, that's under the line, so that's unsaturated. If I have 40, then that's saturated. If I have managed to dissolve more than 40, so in other words, it's not saturated. It's not sitting at the bottom of the beaker, but it's fully dissolved, more than 40 at 90 degrees Celsius, so I'm above the line. That would be a supersaturated solution. The only way to get that is to heat up the solution and then let it cool. And if no crystals form, then those ions will just sort of stay in the aqueous state. And even though there's more than the normal threshold amount, which in this case would be 40 grams, the ions stay dissolved. And so here's a picture of a supersaturated solution of sodium acetate. And so there's more sodium acetate than you would normally be able to have dissolved at this temperature. I believe this is supposed to be at room temperature. And you take some tweezers or tongs here and add a little seed crystal of solid sodium acetate. And what that does is it takes that supersaturated solution, all those sodium and acetate ions, and it gives them something to form a crystal on. So it's a seed crystal. And so that what you see very quickly within a couple of seconds is the whole thing just sort of crystallizes. It looks like it's freezing, but it's really just crystallization of that whole supersaturated solution. Solids will tend to increase usually. There's, you can see here there's one exception here, this last guy here. but most of the time they increase with increased solubility at higher temperatures. So they go up with temperature. And that's simply because more kinetic energy means there's more interaction between the ions. That more of that ion dipole interaction has a chance to happen, pull apart the ions in the crystal and give us an aqueous solution. Now gases, though, do the opposite. So gas solubility decreases as temperature decreases. Okay, and so you can see, for example, if you go up a little bit in temperature from, let's say, 20 Celsius to 30 Celsius, the amount of oxygen that can be dissolved, and this is being measured in millimoles, so a little different measurement, but it's the same idea. The amount of oxygen that can be dissolved at 20, it's gone down pretty substantially when we get to 30 degrees Celsius. And so that has a big impact on, aquatic life. You can't, if your water warms too much, you can't have as much dissolved oxygen for the animals, insects, fish, you name it. You can't have as much carbon dioxide dissolved for your plants that are aquatic and so forth. So, and then here's a little snippet of a question from AP Central. It's asking about the actual dissolving of a gas, namely oxygen. Which model better represents how oxygen dissolves? So maybe pause for a second and think about this. What are they showing in the models? What are they representing in terms of intermolecular forces? And which one do you think is accurate? Okay, so hopefully it makes sense to you that this super organized arrangement of water molecules around an oxygen is not what happens. There's way too much kinetic energy in liquid water and in oxygen, at room temperature for this to happen. Plus, these technically represent hydrogen bonds. And so that's not going to happen with a nonpolar oxygen molecule. Diagram 2 is much better. And what they're showing here is induced dipoles. So you've got your more negative oxygen end of these water molecules repelling the electron cloud away from them, which is why they're showing this sort of, the electron cloud is getting bigger on the right side here. And that is attracting these positive hydrogens from these water molecules on this side. So this is what's happening when oxygen or any other nonpolar gas dissolves in water. Okay, last thing here, let's talk about pressure. So when you open a soda and it fizzes, what's going on? Well, this is governed by something called Henry's law. So here you have like a liquid with some dissolved gas and a piston. So we've got this vapor pressure, this partial pressure due to the evaporated gas. I'm sorry, due to the gas, whatever it is. It could be nitrogen, oxygen, whatever. Or I'm sorry, in the picture it's supposed to be CO2. So we've got some CO2, and if you push down, well, first of all, we have equilibrium established over here because some of those CO2s are becoming dissolved. They're being surrounded by water molecules. Dipoles are being induced, like we just talked about, and they're becoming dissolved. And then some are escaping. So they have enough kinetic energy to escape and go back into the gas state. And it's at equilibrium. We have about the same number of molecules doing each one. If we push down the piston and increase the pressure above the liquid, so the partial pressure of the CO2 above the liquid, that is going to push a greater number of the CO2 molecules into solution. And so you can see 3 little arrows going down and 2 going up now. So we're not at equilibrium. Equilibrium's been disturbed here. And then finally, equilibrium is restored or reestablished. But notice now at this higher pressure, because we've pushed the piston down, pardon me, there are more CO2 molecules dissolved than there were originally, right? And so this is the opposite of what happens when you open a soda, right? It fizzes because you're releasing that partial pressure of CO2 above the liquid in the soda. You're taking it from several atmospheres down to 1 atmosphere, very quickly, and so a lot of that CO2 is going to become undissolved. So this is governed by Henry's law, and Henry's law is just the solubility of a gas, usually measured in molar or moles per liter, is equal to a constant, which is K, times the partial pressure of that gas measured in atmospheres. Um, Henry's Henry's law constant is what this value for K is called. And even though it's a constant, it changes with solvent, solute, and temperature. So all three of those things have to be held constant from one situation to another for you to use the same Henry's law constant. Okay, so it depends on the identity of the solute. So let's say CO2. It depends on the identity of the solvent. So let's say water. And it depends on the temperature. So let's say we're at 25 degrees Celsius. And then you will get a value for Henry's law constant, and it's measured in moles per liter atmospheres. Okay, so let's take a look at this question. What is the concentration of CO2 in soda bottled with 4 atmospheres of pressure over the liquid at 25 degrees Celsius? And the Henry's law constant is 3.1 times 10 to the minus 2 moles per liter atmospheres. And again, that value is specific to this temperature. It's specific to CO2 being the solute, and it's specific to water being the solvent. So go ahead and solve that one. We're looking for concentration, which basically it's another word in this case for solubility, right? Because we measure solubility in moles per liter. So go ahead and solve that one real quickly. Okay. So your solubility of CO2 should be equal to your K value, which was given to you as 3.1 times 10 to the minus 2, times 4 atmospheres. So it's literally just multiplication. And we get 0.124 molar or 0.12 molar. I guess I should have labeled that CO2. So this would be a typical concentration of carbon dioxide in soda. But of course, that's before you open it. When you open it, that's going to leave, right? Because your partial pressure of CO2 is going way, way down.